All right, so our probability we're going to start with is actually basic probability, chapter 14. We'll quiz that the Friday before Thanksgiving. And this first part is probability that you've already done in your life. So it's these kinds that you've already seen before. You probably just saw them way long time ago. So let's get started. So we're first going to talk about some basic definitions and kind of go through an activity to get that. So the first thing is I'm going to take a simple random sample of students in the class, and you don't have to stand up. Just identify who you are, and then we'll use that information here in a minute. But while I'm getting those 10 students' names, I want you to, in this space, create a table of how we would organize this data. Once I get their information, I'll get if they are male or female, and then I'll get if they have blue, brown, or green eyes. If you have hazel, then I want you to pick which one of those eye colors you are most closely associated with. So let's see. While you make that table, let me get my 10 people. So let's do this. But I know that you've got that and it's pretty easy, okay? But I'm getting to a vocabulary word. So if we were to list out all of the possible combinations, then what would those be? One of them, the first combination would be what? A male with blue eyes. And then a what? Male with brown eyes. And then a male with green. And so on. A female with blue eyes, a female with brown eyes, and a female with green eyes. So this is a way to represent and organize and to think about how to get the possible, to get the set of all possible outcomes or combinations. And this is a vocabulary term. This table with all the possible combinations or all the possible outcomes is called a sample space. Okay? So that's a vocabulary term for all those possible combinations and outcomes, just what all could happen. All right, so let's go ahead and reproduce this table and then collect our information of what we actually got. I'm going to include the totals as well of my people here. All right, so let's see here. If you're one of my 10 people, raise your hand. Let's see who's male and female. What do we got here? Let's see. One. Are you one of my 10 people? So 1, 2, 3, 4, 5 males. Nice. So then I have 5 females. Excellent. Each period this day has been 5 and 5 or 6 and 4. So that's cool. All right. So if you have blue eyes, if you consider yourself having blue eyes and you're one of my 10 people, raise your hand. So, wow. So that's 1, 2, so 3 and 3. Nice. So I have 3 males with blue eyes, 3 females. So 6 of my students have blue eyes of those 10. Okay. How many? Raise your hand if you're one of my 10 with brown eyes. Okay. So I've got 2 males and 0 females for a total of 2. So let's see. We should be able to figure out what's left. How many males have green eyes? None, because I already have 5 males. Females, what's my females with green eyes? Raise your hand. Yep, that's my 2 people. Good job. So that works out for a total of 2 green-eyed students. Okay, so there's our data set. From this, now I want you to go and fill out these probabilities you have here. So we know probability is the successes over the total. Successes over the total. So the probability success over the total. And I'm not reducing today because I'm just getting to the point of the numbers, okay? So based on what we've learned this year, would you consider these amounts, these questions, marginal probabilities or conditional probabilities? So, like, for example, if it just asks about male and female or blue eyes, brown eyes, and green eyes, where am I getting those answers? They're marginal. Good, because look, here is my overall male and female, my category, my total of my categories, male and female, and my total of my categories, blue, brown, and green. So yes, those are then considered the marginal probabilities. Okay. It would not be until I ask about blue-eyed males that I'm talking conditional upon you being this. What's the probability you're that? Okay, now I want you to find each of these probabilities and explain why explain why you answer makes sense. Oh, I do have a correction actually to make. So as I do this new packet, I'm like, have a running list of corrections to make. This is not supposed to be an or. I want this to be an and. Okay? So fix that right there because I'm trying to demonstrate a definition. All right? So do those two questions. All right, so what did you have as your probability for probability of the students that are male or female? Yeah, the male is 50% or being a female is 50%. So that means what proportion of my total is, yeah, 100%. Okay. So, and the reason is because all the students are either male or female, hence 100%. And so the main thing I want you to get from this is something we do already know, is that all of the probabilities sum to what? 1, also known as 100%. All right, what's happening here? How many of the students have blue and brown eyes at the same time? 0. So that was a 0%. Because no students have both blue and brown eyes. Now, I do know that's possible. I know there's a pitcher who has, anybody know that one? A pitcher who has blue and green, I think, shirt. Yep, that's right. Of course, you'd know that. I was thinking Herschel today, but because I got the sure in there, but I couldn't remember his name. All right, but I'm demonstrating for you a new vocabulary word, which you probably are not familiar with, and that is disjoint. Disjoint is an important idea that we will discuss, and it'll become even more important after Christmas whenever it actually matters. You have to identify if something's disjoint or not. And what disjoint means is, any ideas what disjoint might mean based on that example? Okay, yes. No outcomes in common. There's no intersection. If I was drawing a Venn diagram of this, blue and brown eyes, it would look like two separate circles that are not joint. Hence, disjoint. Okay, not joint. Two separate circles, no overlap. All right, and this is the type of probability we're going to deal with until we get back from Thanksgiving. These are much simpler. All right, moving on. on this one, we've got some issues because these top two may not be disjoint depending on our data. So I want you to take a look at the first one, probability that you have male or blue eyes, and then the second one, female or brown eyes. And so let me leave this up so you don't have to flip back and forth, but I want you to try those first two on the top of the next page. Okay, try that now. I'm going to give you 1 minute to do, actually you could do all four of those. 1 minute to do all four of those. There's your data. Okay, so time is up. So let's see how you did. I heard some good discussion. Okay, because apparently we do not have disjoint events. Like, for example, in order for male and blue to be disjoint events, that would mean there's what? No males who have blue eyes. And we have that, so not disjoint. Okay, so how are we handling that? Male or blue eyes? Because what happens if I go add 5 plus 6? That's 11 out of 10. What the heck? How can that happen? You can't have 11 out of 10 people being a male or blue eyes. So what's the deal? If I added males plus blue eyes, what just happened here? There was overlap, and these 3 blue-eyed males got counted twice. That's the problem. So what we'll end up seeing, and we'll talk about this more in depth after Thanksgiving, is that when we have if we added all of those males plus all of the blue-eyed people, we had double counting, and we had to take away those 3 blue-eyed males because these got double counted. So there's a couple of ways you can do this. You can say, okay, what was there? 6? Was there 6 males?
There's 5.
Oh, 5 males plus 6 blue-eyed. Oh, wait. Oh, then there were 3 that got double counted for a total of how many? 8. So let's reevaluate that. So let's see. So over here, I'm going to do this in orange. This plus this plus this plus this. Those orange circles are 3 plus 3 plus 2 plus 0 for a total of that 8. Okay, so you can either add up those individual ones, or you have to do that other little fancy formula thing, which we'll get into later. Okay, how about the next one? What was it? Was it female brown-eyed? That was interesting. Tell me about female brown-eyed. Are they overlapping or disjoint or what? There are no female brown-eyed. So in our particular class, our female brown-eyed ones were disjoint because there was no overlap. That made our job very simple. So because this is perfect example, because there is no overlap, it's really easy. We can just add all the females plus all of the brown-eyeds oh, that's brown, and then this was blue. Okay, we can do that, and then we get our answer because there wasn't any double counting. So female was 5, brown eye is 2, so that's a total of 7/10. 5/10, 2/10 for a total of 7/10. Okay, nice. All right, the next one is I want to demonstrate a vocabulary word here. Not. What's happening if I want to do the ones that are not green eyes? Yep. Okay, then I'm going to do all of the ones that are green eyes and subtract it from 1. Okay, so how many green-eyed people did we have? 2. So if I have 2 green-eyed ones, then 1 minus the 2/10, how many did I have that were not green-eyed? 8/10. Okay, this is another vocabulary um, time that I can talk to you about this thing called the complement. Okay, the probability of green eyes complement means the not green eyes. The complement of green eyes is not green eyes. So anytime you have a complement, that is 1 minus the probability of that event happening. So it's like, what's the probability of something not happening? Well, it's 1 minus the probability of it happening. Okay, so I'll say that again. The probability of something not happening, that's the complement, is 1 minus the probability of that event happening. Okay, so let's take a look at the males. What's our complement of males? Not males is what? Females. Okay, so the complement of males is females, which did we have 50-50 in here? 5 out of 10. Okay, very good. And finally, here are some of just the definitions. I think the most interesting one is this one, random. Gets me every year. I pull that out and I'm like, oh yeah, dang, that's weird. Because when we think random, we think of like chaos where, you can't tell what's happening. Okay? And that's true. What is it? Read this definition to yourself and see how that's kind of different than just pure chaos. Coin toss. I'm gonna flip this coin. What's probability? What am I getting next? Do you know what I'm about to get on my coin toss? No, the outcome is not known. But in the long run, what proportion of times am I going to be getting heads on my coin? 50%. Yeah, 50% of the time, half the time. So see, the initial next outcome, you don't know, but in the long run, you can determine what it is. So that's interesting that's that randomness. We've already talked about probability, sum, sample space, and we'll go dive more, and we've done complement. We'll dive more into this disjoint and independent as we move through the unit more. Let's go to this next one. All right, now we got to work. The best way to get this probability is to practice, practice, practice. I do not give you busy work. I abhor busy work. And so therefore, if I'm giving you problems to do, it's because I have to expose you to all the different ways that you can say the same thing. And you just have to practice it, practice it, practice it. So there's no way of getting around it. So let's take a look at this first one. This first chapter, 14, is independent probabilities and disjoint probabilities. For independent probabilities, we can take an event happening and multiply them together. So we take the probability of the first event happening and the second event happening, and we can multiply those together. So when they are independent, the way that those happen together is you are going to multiply, and we are going to multiply. Flipping a coin. What does it mean to be independent probability, by the way? They don't rely on each other to happen. You're on the right track. The fact that the first one happened, what? Does not change the probability of the second. Flip a coin. Is that result affecting flipping a coin's result on the second flip? No. Independent. The fact that you are one thing does not change the rate. Okay. So let's do this. If I want to find the probability of flipping a coin and getting heads 2 times in a row, I have 2 events. The first event and the second event. So I want heads on the first event and heads on the second event. So how does that look mathematically? What's the probability here? Heads on the first one and heads on the second one. That's 1/4. Okay. How many events does question B have? What's the probability of scoring a total of 18 when 3 fair die are rolled? What's that? How many events is that going to have? How many trials or occurrences? 3. I'm going to have 3 actions. I'm going to roll a die, and then I'm going to roll a die again, and I'm going to roll a die again. So here's a hint. How can you get a sum of 18? 6 plus 6 plus 6. Okay, so there's your little hint. It's evil problem. Okay, so I'm going to let you work through this. And then I'm going to let you do part C, and I think you can do D. I want you to finish this. I'm going to give you about 4 minutes to do those. Go. So then what we have, of course, let's go back, getting a 6 on part B. What's the probability of getting a 6? Rolling a 6 was, okay, 1 6, 1 6, then 1 6. And, you get 1 out of 216. Now, some people want to start showing shorter work than writing all of that out, and that's fine. But you have to show work. You cannot just put 1 over 216. As short of work as you can get would be if you wrote it like this, 1/6 to the 3rd power. That's as equaling 1 over 216, or you can do it as a decimal, whichever. But you have to show something of how you came up with your answer. How about this one? The probability that you roll a die and you do not get a 3 until the 5th roll. So not a 3. What's the probability it's not a 3? Okay, so these are all 5/6. Not a 3, not a 3, not a 3, and then ding, 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 you get your 3. So the shortest way you could write this is 5/6 to the 4th power times that winner of 1/6. Okay? All right, and then we talked about this a minute ago. We have a 5 multiple choice question quiz, so there are 5 events. That's why I have 5 blanks drawn, because they each represent the question on the quiz. And since you have 4 possible answers, the probability that you get one correct, just random correct, is 1/4. So what is it for it to be wrong? 3/4. So we have 3/4, and we have 5 questions. So you could write it all out. 3/4 times 3/4 times 3/4 times 3. So the first one's wrong, and that's multiplication. The second one's wrong, and the third one's wrong, and the fourth one's wrong, and the fifth one's wrong. How about 100? What do you have to do to get 100? All correct. So I have to have 1/4 and 1/4 and so on and so forth. 1/4 and 1/4, so on and so forth. Okay. All right. Now this last one's interesting. You get the first incorrect answer on the 4th question. So let's discuss what this tells me. The first question is then what? Correct. So that's 1/4. And the second question is correct. And the third one is correct. And the fourth one is incorrect. What's happening on the 5th one? They did not specify. So you can completely leave that off, or, you can think of it like this. Who cares? They didn't tell us. So it could be right or wrong. What's the probability of the question being right or wrong? 100% right or wrong. 1/4 plus 3/4, 1. So see, that's why that last one doesn't matter. They didn't specify. That's why you can leave that off. Now, let's go into parts 2 and 3. Part 2 is going to be talking about this new word of or. And we're going to have disjoint events. What does disjoint events mean? I'm asking about a jack or a queen. Why is a jack and a queen considered disjoint? You can't be both at the same time. You're a jack or a queen. You're not both. Okay, so we have disjoint events. So when you have disjoint events, or is meaning that you are going to be adding those scenarios together. So on this first one, what is the probability that you pick a card out of a standard deck that is either a jack or a queen? So first of all, how many events do I have? It's not like 5 multiple choice questions. How many events? 1. I'm picking a card. So I have 1 event. See? I have 1 event, and I want it to be a jack or a queen. And so I'm going to come around and pass out to you the things, but there's 4 jacks and 4 queens, so that's 4 plus 4 is 8. See, that's how you're getting a jack or a queen. And you can reduce this, of course. I'm just giving you the main answers so that you don't get that confused. And so I'm going to leave these parts 2 and 3 for you to do, and I'll also come around and pass out to you a picture of the deck of cards if you don't know exactly what's in a deck of cards. All right, so do those. I'm going to give you 5 minutes for that. Okay, there's your simple ones about the cards, 852 and 3652, and you can reduce. But here is where it gets interesting. Okay, you roll a die 3 times and you do not get a 1 or a 6. So see, this is 1 6 plus 1 6, hence that's a 2 6 probability of getting a 1 or a 6. That's what makes not a 1 over 6 or 1 or 6, not a 1 or a 6, and then a 1 or a 6. That's your 2 6. And then however that reduces. Same thing here. Not a 1 or a 6, not a 1 or a 6, a 1 or a 6, and they say you're rolling it 5 times. What's going on here? Who cares? Anything. So you don't have to put them on there. Anything, whatever. Okay. So I wanted to show you this because I wanted you to see that there's even there's infinite number of ways to say the same thing, and you have to be able to figure out those different ways that you can say that. All right, but this last one is really interesting. You are rolling this die 5 times, and so what's the probability you're getting your success on the 3rd or the 4th? So a lot of you picked up on that or, meaning that we're going to do what? Okay, so what are we adding together? Both of those ands. So what is it that we're adding? Success on the 3rd with the success on the 4th. So this is actually the number 1 most missed question on this unit exam. Okay, so I really want to point this out to you, and we have this show up frequently throughout our packet. Here is the most common wrong answer. Here we go. Oops, I wanted to do this here. Dun, 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 dun. Here we go. Bam. That's wrong. Bad. Wrong. I get what you're thinking. You are thinking, hey, success on the 3rd and success on the 4th at the same time. But that's not what it said. What did it say? Success on the 3rd or success on the 4th. So that was 2 separate success events occurring. Okay, so that's that difference. Okay, so of course we have our 5 6, 5 6, 1 6, or then you have 3 of these. Okay, all right, so those are very close in wording. Very close in wording. All right, questions there. We have one last little topic that I'm going to slam at you in these last 6 minutes. Your assignment is pages 5 and 6, which we've already discussed, but let's go to this last idea. Here we go. Okay, so we have this situation where we have a whole lot of combinations we want to deal in an efficient manner. So talk to me about this one. Actually, read the first one. You know it. Do it. Go. Okay, you're 1/4. But now our new vocabulary today, our sample space. I want you to list out the sample space for that situation. So talk amongst yourselves. Do those sample space. That's the list of all possible outcomes for 2 coins. List of all possible outcomes for 2 coins. Well, like heads, heads.
Yeah.
Heads, tails. Yeah. So how many possible outcomes are there? There's 4. All right. Well, guess what? Can you identify from this how many outcomes listed above by just looking at this sample space have 2 heads in a row? How many? 1 out of how many possible outcomes? 4. Dun, 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 dun. That's where that comes from. Okay, but here's where it gets interesting. I'm going to sometimes be asked for all the other stuff. And unless I actually draw out all of those different ways, it's hard to compute how many of these other things there are. In this case, how many of these situations show at least 1 tails? How many of those show at least 1 tails? 3 out of 4. Okay, so that was easy because I have it drawn out. How could I have done this problem only knowing this? Just knowing the no tails. This is the one time no tails happens. How could I then get this other part from only knowing no tails? Yep. It's 1 minus that probability of no tails on the 2 flips. So if from the beginning I asked you, what's the probability of at least 1 tails? You'd be like, oh my God, I don't know. I'd have to list all this out. But I could go 1 minus the probability of no tails. And how do you have no tails? Heads, heads. And what does heads, heads looks like? Half times a half. See, I can compute that easily. So there is the answer without having to list all of the combinations out because they can be insane. For example, what if you had to list out the sample space for 4 coins? That's pretty bad. You're going to have heads, 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 and so on. Do you know how many total combinations you have? You have 16 total combinations. So if that's the case, how can you identify at least 1 tails? At least 1 tails is everything except for what? You want all of these, but just not that. That's at least 1 tails. So how can I mathematically do that? 1 minus the probability of none of the 4 are tails. Okay, do that math. Anyway, that's how you would do it. 1 minus, in order for them all to be heads, it would have to be half times half times half times half. Okay, let's quickly go through 2 examples. A, you toss a coin 3 times. What's the probability you get at least, oh wait, no, I'm sorry, it's a die. It's a die. 1, 2, 3, 4, 5, 6. You want at least one of them to be a 1. So that's every single thing except for what? Everything except for what happening? A 1, a 1, and a 1. So this should be 1 minus the probability of None of the 3 tosses is a what? 1. So FYI, what's not a 1? 5 out of 6. And I want that to happen 3 times. So whatever that is. If you want to stay for another minute, I got one more for you. Otherwise, you can go. 13% of the population is left-handed. What's the probability at least 1 out of the 10 is left-handed? 1 minus the probability that none of the 10 are lefties. If none of the 10 are lefties, what does that say about them all? They are all righties. So that's 1 minus. How do I notate all of them being righties? 0.87, and there are 10 of them. So whatever that comes out. All right, so pages 5 and 6 are your homework. I'm sorry that last thing gets kind of crammed up there at the end, but we'll continue going over that tomorrow.
Are there a lot of songs for this? Or not really?
So I do